Mm, Okay, good morning, everyone. Welcome to this guest lecture. As you know, this week and the next week, we will have two guest lectures. And this is about how to conduct the mini project. So first, let me just clarify one thing, because I have received a couple of inquiries from some students. For this mini project, this is a group work, and basically we can permit maximum 2 students in each group, and each group must complete all the tasks. That means 2 problems and 2 virtual labs. Okay. But for the you will submit a written report and also a short video presentation. But in this short video presentation, because we ask you to submit a video presentation for 3 minutes. So in this video presentation, only 1 problem or virtual lab needs to be selected for presentation. I know some students have experience with MATLAB, but some students might have only a little experience or even no experience with MATLAB. So I invited Bradley from MathWorks to deliver these 2 guest lectures. Bradley has provided us with great help in the development of the mini project, and he has developed all the codings for us. So basically, in this mini project, you will use MATLAB as a tool for this mini project, but you don't really need to do any programming and coding. Of course, you still need to know some fundamentals about MATLAB. Okay, so now I'm handing over this to Bradley. Bradley, please start your guest lecture, and probably you can have a introduction for yourself. Thank you.
Yeah. Thanks, Dongbin. Look, the first thing I'm going to do is I'm just going to share my screen.
Yeah.
And I'll just ask you just to confirm that you can see my screen.
Yes.
Oh, great. All right. And look, my second question is, I was planning to stop at approximately 10:50 to 10:55 a.m. Is that appropriate, or is that too late?
Yeah, that's okay.
All right. Okay. All right. Well, look, good morning, everyone. As Dongbin mentioned, my name is Bradley Horton. I'm one of the engineers at the MathWorks Australia office. Let me give you my 10-second bio. So when I was a student, I did a double. I did mechanical engineering, and I also did applied maths in a science degree. My first job was at Defence Science Technology Organisation down in Melbourne. I was a systems engineer, and I sort of developed and maintained software models of air vehicle systems, aircraft dynamic models, avionics systems, and so forth. I've been at the MathWorks now for about 18 years. So I've used a little bit of MATLAB and Simulink. So before we actually get into the MATLAB and Simulink stuff, I just want to sort of be very upfront about the objectives of this 2-hour session that we have together this morning. So the 3 objectives are, we're going to sort of open up some example case studies in MATLAB and Simulink. We're going to get you really comfortable with how to do that on your own. We're going to run a selection of those case study example files. Again, making sure that you're really comfortable being able to do that after this morning. And the third one is, yeah, look, we're going to give some explanations on what it is that we're trying to do with those engineering case studies that we're actually analyzing, simulating, and modeling. All right, so look, let's start. I don't have any PowerPoint. We're going to jump straight into MATLAB. So I believe you've all been given a heads up that there is a zip file that you were to download and unpack, because that contains all of the examples that we'll be using this morning. So I'm hoping that you've been able to do that. The zip file was moderately large. It was around about 193 meg. So as I'm sort of chewing into our time right now, if you have not if you have not downloaded that zip file, you better start doing it. It is absolutely essential for what we're about to do next. So I am going to assume that you have indeed downloaded the zip file for this morning, and you've just placed it in some sensible folder on your laptop. All right. So this is step number one. Go and get that zip file. So the second step is we're going to launch MATLAB. All right. So I'm actually going to be using the R2023B release of MATLAB. For those of you that are after a little bit of barbecue trivia, since 2006, we've released a version of MATLAB every April and every September. And we call them the A release for April and the B release for September. Every 6 months since 2006. So the latest version of MATLAB is actually R2024A. It came out late March, early April. You're welcome to use that version if you've got that installed, but I'll be using the 23B release today. So yeah, look, just launch your MATLAB release. If you are using an older MATLAB release, you may have some problems opening up the Simulink files that were developed in a newer MATLAB release, the 23B release. But if that happens, I'll be monitoring the chat, so yell out to me, but I'm just giving you a heads up. All right, so you've launched MATLAB, and for those of you that are kind of new to the MATLAB desktop, let me give you the 5-second introduction. This is the MATLAB desktop, and it's made up of a series of panels. On the left-hand side of my screen, you can see the current folder panel. It's very, very similar in behavior to the Mac Finder and the Windows File Explorer. Another panel that's on my desktop is the Workspace panel. And this is where you'll see MATLAB variables that get created when we run some of the scripts that we're about to look at. And sort of the third main panel that I want to talk to, at least at this stage, is the command window panel. We'll be using these panels very, very quickly. So look, I think the very first thing that I'm going to do is I'm just going to sort of interact with this sort of folder, sort of breadcrumb sort of widget. And this is just going to help me navigate into the folder where I downloaded the zip file for this morning. So I'm just going to sort of click on C, because it's the C drive where I've placed my stuff. I've got a folder called BH. I'm sure you guys will figure out how to navigate this folder panel. And I'm going to sort of double click into finally the folder, which is on my computer, at least this one, where I downloaded the zip file. So this is the zip file. All right. So once you've sort of navigated, and again, I just want to make sure that everyone does a stop and stare moment. I'll ask for some input from you in the chat window in just a moment. But I'm hoping that everyone has launched the MATLAB desktop. You've been able to navigate to wherever the folder is where you have downloaded the zip file. So folks, if I can just give you all maybe just 2 minutes to sort of get to this stage. And when you have, can you just type me a really short message into the chat, words to the effect of ready to go. So let me just give you just a couple of minutes. All right, great. Thanks, Tim. All right, there's one down. Dongbin, one of the students has asked, look, wasn't quite
Zip
sure.
file.
Yeah.
Okay. If you look at the canvas site, you will see the folder of MATLAB under the module of resources, and in that folder you will see the link for all these files.
All right. So Tim is ready. Andrew is ready. Young is ready. Matthew is ready. Give it just another minute or two. Thanks, Dylan. Thanks, Alan. Thanks, Ashley. All right. So look, it feels like we've got quite a few students that are ready to go. How many students do we have on the call? We've got approximately 50 people. I think we've got approximately a dozen have said ready to go. So look, I'll just wait one more minute, just one more minute. Thanks, Daniel. Now, you all know that this is being recorded, so obviously you're able to rewatch this after we're done this morning. But as much as possible, I'd like this to be a sort of collective sort of session that we all sort of work through this together as much as possible.
Yeah.
Thanks, Anthony. Okay. Again, if you have done this, got yourself to the stage where the MATLAB desktop is open, you've navigated to wherever the folder was that you downloaded the zip file, just type in ready to go into chat. I'm counting approximately 13 people out of 48. So by no means are we even at the halfway point yet. Thanks, Lachlan. Thanks, Fergus. Dongbin, do you think I should just maybe wait just another minute or two? I think we're slowly getting to approximately half of the audience is ready, but half aren't.
Yeah, let me have a look. Yeah, about half. Yeah, okay. Please wait for one more minute.
For those of you that have, here's going to be the next step. All right. So from MATLAB, we're actually going to unpack the zip file directly from MATLAB. Okay. So to do that, just locate the command window, right? And it has a blinking sort of prompt, and you're going to type in the MATLAB function unzip, all right? Open and close parentheses, and you'll specify as a single input argument to the unzip function something that is enclosed by double quotes, the name of the zip file, right? So on my computer, the name of the zip file is master_mma.zip. It may or may not be the same name zip file that you have on your system, but whatever it is on your machine, just use the name of that zip file. So just type in this command, unzip, exactly as I have, and hit enter. And this will make MATLAB unpack the contents of that zip file. If you have any problems using that command, please give me a shout out in the chat. All right. So once you've typed in that unzip command into the MATLAB command window, so once you've actually done this, you should notice that there is a folder that's just been sort of created. The folder is called master. And what I want you to do now is just navigate into that master folder. Again, just interact with the current folder panel on the MATLAB desktop and just double click. So as a reference, here's my present working directory sort of summary. And you can kind of see that here are the folders. Here are the folders that are now contain all of the case studies that we're going to be looking at today. Alrighty, so look, I'd really like to sort of get started on this. Dongbin, do you think it's okay to move forward, or do we wait just another moment just for the remaining?
Yes, please make a forward.
Okay, alrighty. So folks, there are sort of 4 case studies in total that we'll be looking at during today and next week. We'll be covering 2 of those case studies today. So let me sort of just give you a heads up as to what we'll be looking at today. So today we'll be looking at that sort of classic example of a steel cylinder that's unsecured on the back of a truck bed. We'll look at what happens when the truck sort of accelerates. What does the spool do? Does it roll? Does it slide? And the second example that we'll look at today is just a reminder of one of those really nice engineering and physics sort of concepts called the principle of impulse momentum. So we'll be doing a virtual lab. So these are the 2 case studies that we'll be looking at today. So the first one is going to be the spool on the truck bed. So if you can, again, just navigate into this folder, just double click on spool on truck bed. And again, just to orientate you, your present working directory on your installation of MATLAB, at least the very last folder that is cited, it should say spool on truck bed. So it's really important that you give yourself a big tick and confirm that that's where you are right now. The way that the files are displayed in your current folder might be just a little bit different to how they are on mine. So if you click on the little sort of, I don't know what sort of badge you'd call this, but it's up in the right-hand corner of the folder panel. It'll bring up a context menu, and the context menu gives you a choice to display files according to their file extension. So if you just sort of click on group by and select type, that will make your folder panel display all of the script files together, all of the Simulink files together, etc. So have a go at just doing that. Alrighty, look, let's get into it. Let's rip in. So the file that I would like you to sort of open first is, of course, the one that says demo start here, please. So if you can just sort of find this file and then double tap on it to open this file. It's going to be a MATLAB script file. So demo start here, please. All righty. So I'm double clicking on it and here it is. So I'm hoping that for most of you, when you double click on that file, it has actually embedded the file into your MATLAB desktop, right? So the editor is now another panel, if you will, that appears in your MATLAB desktop. I'm going to try and sort of utilize as much of the screen real estate as I can. So I'm just going to walk up to this sort of part of the embedded editor, and I'm just going to, again, double tap. And this will, well, I think cause and effect is the easiest way to explain it. This will just make the editor panel occupy almost the entirety of my MATLAB desktop. If that concerns you, you can just sort of double tap on that blue region once again, and that will sort of bring it back to not monopolizing your whole MATLAB desktop. All right, so here it is. So this is the start here script, and this is going to help us sort of launch some of the analysis tasks that we're about to do. So firstly, let's get introduced to the case study. I hope the animation is coming through during this Zoom broadcast. But here's the system that we're going to be exploring. We have a yellow truck bed, and sitting on the truck, the back of the truck, is an unsecured cylindrical sheet, rolled sheet of metal. It's unsecured. So the significance of emphasizing unsecured is that clearly, as the yellow truck bed accelerates to the right of the screen, the unsecured cylinder spool will roll, slide off the back of the truck bed. So this is the system that we're going to be looking at. Yeah. So we'll do a stock standard Newton's second law equation of motion derivation. Right. So this will provide us with the fundamental equations, which we will then apply to do an analysis. The two analysis tasks we'll consider the scenario where we'll make an assumption that the spool does not slip, that its motion is pure rolling. Then we'll do another case study where we will make no such assumptions. It will be our responsibility to determine if the spool is sliding or purely rolling. And the last thing that we're going to do is we're going to open up a Simulink simulation so that you can actually see an engineering model of this being simulated and visualize the behavior. All right, so let me just sort of scroll down this script. There are 3 tasks. We're counting at 0 today, I'm afraid. So task 0 will be the equation of motion derivation task. We'll get to that in just a second. Task 1 will be an analysis task where we study the system under the assumption of no slip. And task 2 will be another analysis task where we will have to decide on what the state of the spool is. Is it sliding, slipping, or is it rolling? So 3 tasks. So let's start with task 0. Let's have a look at where do the fundamental equations come from that we'll be utilizing this morning. So hopefully you can see a hyperlink that's embedded in the script. So I'll ask you just to click on this hyperlink, and this will open up another file for us to start looking at. Alrighty. So just to give you a little bit of orientation, I'm hoping that you all still have your start here, please script open. But what just also opened when you clicked on that link was this second file. So let's focus on this derive equations of motion for the truck and spool. So we're going to derive the equations of motion using Newton's second law. All right, so let me sort of introduce you to a couple of the parameters that we'll be utilizing. Let's start with this sort of graphic. So we have x1 is the degree of freedom for the truck bed. So in our subsequent derivations, you will see expressions such as x1 double dot, and this denotes the acceleration of the yellow truck bed. We'll use x2 to denote the position of the center of mass of our spool. And the other degree of freedom that sort of categorizes the pose of the spool is the angular one, theta. So theta is the angle of the spool relative to the horizontal inertial axis. So x1, x2, and theta. So like all engineers, you are drilled into drawing your free body diagrams and then using the free body diagrams to develop the derived equation of motion. So let's see if we can get sort of agreement on what the free body diagram looks like. So I'm hoping that when you look at this diagram, that it contains all of the forces acting on the spool. And please yell out if you're in disagreement here, please. So you've clearly got the mass of the weight of the spool, the weight force. You have the reaction normal force from the truck bed. And you, of course, have some sort of frictional force that's trying to rotate the spool. So I put it to you that that is the free body diagram for the spool. And although I forget off the top of my head what you call this diagram, but this is just a reminder that, of Newton's second law, that once you draw the free body diagram, that thing is equivalent to saying that the system has an acceleration and the system has an angular rotational acceleration. All right, so that's our free body diagram. And just a few more sort of symbols, just to make sure we're all on the same page. N denotes the normal force. FF is the frictional force. I think we've already talked about our degrees of freedom for the spool. M is the mass. And IZ, this one does deserve just a moment to stop and stare, because you can take inertias of rigid bodies about any arbitrary point. IZ in this context is the moment of inertia of our cylindrical spool about its center of mass. So that's what IZ stands for. Alrighty. So we've got our free body diagram. We're going to take advantage of what Newton did a couple of centuries ago, and we're going to apply Newton's second law. So what we're doing now is independent of whether or not the thing slides, slips, or rolls. Right? This is Newton's second law. So you've got Newton's second law acting on the spool in the horizontal direction, and there's only one force acting on the spool in the horizontal. We can take the moments of all of the forces about the center of mass of the spool, and when we do that, it actually eliminates a lot of stuff. All of the forces that pass through the center of mass get eliminated, and we're of course only left with the frictional force. Yeah. So that's this equation. We can also take moments from our free body diagram about the contact point between the spool and the truck bed. Yeah. So if you sort of walk up to this free body diagram and take the sum of the moments acting about this point, we'll get an equation. And just while I'm sort of zoomed into this graphic, we can also repeat that. Let's take the moments about point B on this diagram. So let's have a look at those two equations. So here's the first equation, yeah, and here's the second equation, right? And of course, the sum of the moments, regardless of which diagram you look at, about that point will have to be the same. So from that, we sort of deduce that that this is another equation of motion. And you can kind of see that it sort of couples the angular rotation of the spool to the translational acceleration of the spool. All right, these Newtonian sort of equations of motion we're going to use in just a moment, but these equations apply regardless of the rolling or slipping state of the spool. So now let's start considering some very specific scenarios. Yeah. So the first scenario that we're going to look at is the assumption that the spool does not slip. All right. So the significance of this assumption is that the acceleration of point B that is on the spool, that acceleration at that point will be the same as the acceleration of the contact point on the truck bed. Or using the symbols that I've drawn, the acceleration of B is identical to the acceleration of B double star. Yeah. So with that sort of statement, we can now sort of use it along with our well-established sort of kinematic expressions. So let's start with this one. The acceleration of point B on the spool is equivalent to some point that we know about. The center of mass is a good one to choose. Then added to that, the acceleration of our point of interest relative to the point that we know about. So when you substitute into that sort of fundamental sort of kinematic statement, we get the acceleration of our point B, which we've ascertained is the same as the acceleration of the truck bed, is equal to the acceleration of the center of mass plus the relative acceleration of point B relative to that center of mass. Yeah, and this sort of gives us again a nice sort of coupling expression relating the translational acceleration of the spool center of mass to the truck beds and also the angular acceleration. And I think you can kind of sort of guess where we're going with this, because we're going to sort of take that sort of relationship and we're going to plug it into one of those Newtonian sort of expressions that we derived earlier. And when we kind of do that, we get a nice single expression that relates the angular acceleration of the spool directly to the truck bed. Yeah. Now, I know what you're thinking. Some of you might be really uncomfortable that we had the audacity in the first place of making the assumption that it did not slip. So how do we check that assumption of no slip was valid? How do we know that was true? Well, let's sort of stick again with the Newtonian sort of equations that we derived earlier. For instance, let's just go back to that classic F equals ma in the horizontal direction. And let's sort of substitute what we already know. And when we do that, we get an expression for the friction force that is acting on the spool. Now, you guys already know from perhaps even first year that the friction force of a body that does not slide is related to the static coefficient of friction. And that static coefficient of friction, when multiplied by the normal force, gives us the active friction force. And that action friction force can actually expand or contract, but it does have a limit. And that limit is the friction coefficient times the normal force. So if our assumption of no sliding results in a computed friction force that is greater than what the maximum limit is, then we know our assumption of no slip was wrong. So that's really good. That's really good. So the second scenario is, well, let's assume that the spool is slipping. All right. So what do the equations of motion look like for the spool is slipping scenario? So the most important thing about this scenario is we no longer can say that the acceleration of point B on the spool is identical to its contact point acceleration. We can't make that statement. The two things are not the same. Yeah. So given that we can't do that, then we need to go back to the safe place, which is Newton, right? What does Newton's second law tell us? Yeah. So we kind of go back to the Newton equations of motion. Here's one, right? And we also have our other angular Newton equation of motion. And remember, right now, the thing is rolling and sliding, right? So what we know is that in that event, the friction force is now related to the normal force by the kinetic coefficient of friction, right? The thing is sliding, yeah? So we substitute what we know about the friction force directly into our Newton equations of motion, and we now get two equations of motion, right? We get one that sort of characterizes the translational acceleration of the center of mass, and we get one that characterizes the angular rotation of the center of mass. All right, so that's the derivation. This is where the equations come from. We're going to be using these equations during our two analysis tasks. It's always good to know where the stuff came from, right? So this document that we've just been looking at together, if I just sort of scroll to the very top, it's nice, right? Because you can include all of your storytelling components. You can insert sort of nice JPEGs. You can have mathematical markup. It's a really sort of informative sort of document that sort of captures your thought processes. But it's not just a document to read. It's actually a MATLAB function. We don't actually sort of reveal that until the very end, where at the very bottom of this file, we're actually seeing MATLAB code. So this function, it has two usage modes. Here's usage mode number one. In a moment, we will call this function where we supply numeric values for the spool mass, the spool radius, et cetera, et cetera. And when we invoke the function with this calling syntax, the assumption is that the spool is not slipping. But we can also sort of invoke this function using a second calling syntax. And if I can just sort of come back to it now. So if we invoke this same function, but we also provide the two coefficients of friction, then the function will determine what the slip state is, and it will utilize the appropriate calculation. So this is the MATLAB code that implements the analysis that we just derived about 5 minutes ago. So as I continue scrolling through this function file, I'm hoping that you can clearly see now that further down the document, we have a subfunction that implements our no-slip calculations. So here's a summary of the relevant no-slip calculations. And here's the MATLAB implementation of those calculations. And at the very, very bottom of this file, we have, again, the relevant equations for the scenario where the spool was slipping. Here are the appropriate equations that we've derived. And here's the MATLAB implementation of those slipping equations. So great. So this is the first task done. This is where we derive the appropriate equations that characterize the spool on the back of a truck bed. Now let's apply these calculations to do some analysis. So I'm going to go back to my start here script. Here it is. So this piece is done, folks. Right? So we were just sort of reviewing this document. So let me sort of scroll down now to task one. So this is going to be the next task that we sort of start to do together. Now this task assumes no slipping. All right, so I want to be very upfront about it. We will assume right from the get-go that the spool does not slip. So let's see what we can do with the calculations that we've derived. So click on this link, this task 01 link, and it'll open up for you our analysis script for this no slip analysis case. Alrighty, so again, I'm hoping that you've still got your demo start here script. You've still got your func spool truck calcs file, but now a third file is opened. The task 01 analysis no slip file is opened. So let's have a look at that. So as we've said, we're going to make the assumption that the spool does not slip. All right, let's see what we can do. Let's just sort of scroll down the document. We've just derived the very equations of motion for that. Here they are. What we're going to do first of all is we're just going to implement those equations in the script itself, and then we'll utilize the function. All right. So let's just scroll down to the very first line of code in this document. Let's have a look at what's going on. So line 1, folks, in the script invokes the clear command, and this simply deletes any MATLAB variables that may currently exist in your MATLAB workspace. So it's always a good practice to sort of do that. And then the next few lines, hopefully you recognize that the symbols that are defined from lines 2 to 8. We're defining the numeric value for the mass of the spool. We're calculating the inertia of the spool about its center of mass that comes out of the screen. And we're also specifying the constant acceleration of the truck bed. Yeah. So we now have numeric values for all of the parameters that characterize this engineering system. And let's take those numeric values and let's plug them into these expressions that we derived 10 minutes ago. So lines 9, 10, 11, and 12 simply implement those no-slip equations. So let's run this sort of section of code in the script. So what I want you to do, and I'll do this really slow, and I'll ask that you stare at my screen very carefully, is I just want you to click on line 2, right? So when you click on line 2, I'm hoping that you now see a blue strip on the far left-hand side of the editor. This blue strip, it gives you some feedback that this section is the currently selected section, right? And now that you've actually clicked in this section, you've got the blue bar appearing on the left of the screen. I want you to click on that blue bar, right? So as you move your mouse cursor onto the blue bar, the cursor changes from a pointer to a finger clicker. Click on that blue strip. When you click on that blue strip, it will run the MATLAB code just in this section of the file. And the word section means that the document has been partitioned into sections. And these sections are characterized by these little blue lines, right, that are visible in the file. So we're not executing the whole file. We're only executing this section of the file. And when you do that, you'll see some results echoed into the output panel of the script. And that's sort of shown on the right-hand side. So on my screen, I've kind of lined everything up, and what it's sort of showing you here are the sort of results that were produced by these calculations that we just implemented. And you'll also see in this section of the file that we executed, we actually invoked that function file that we looked at 10 minutes ago. And you'll see that we provided that function file with the MATLAB variables that contained all of the sort of parameters. And you'll see that because we omitted the 2 coefficients of friction, this function file assumes also the no slip condition, which is why the function's answers are identical to these answers that we manually implemented in the script. So good. It's good to know that we've sort of implemented those calculations correctly. All right. So you might be asking yourself, well, what was the whole point of writing out the expressions in the function file? So the function file that I'm referring to, folks, is this one. Why do that when you can just as easily implement the calculations in the script? Well, one answer for doing that is the old adage that says if you're gonna use a series of computations many times, then it's always a good idea to have those computations defined in one central location, because that means if you need to modify the computations, if you need to make edits to the MATLAB code, you only need to do it in one place, rather than chasing around multiple files where you may have copied and pasted a block of code. So that's the reason. That's the reason why we've implemented the calculations in a function. So now we're actually going to sort of use that function to do something useful. The previous analysis that we just did was for one specific scenario where the truck bed acceleration was 3 meters per second. Why don't we repeat that analysis for a whole bunch of different acceleration values, right? So for example, why don't we consider a range of accelerations of the truck bed from say 0.1 all the way up to 10 meters per second squared? So line 14 shows the MATLAB syntax for defining a numeric array that starts at 0, increments in steps of 0.01 and goes all the way up to 10. Yeah. And the next sort of interesting code fragment is just a stock standard MATLAB for loop that is going to iterate over our acceleration array. It will extract the particular acceleration of interest, and then it will take that particular acceleration and will feed it into our function to calculate the spool forces and accelerations. So let's run this section of code and let's sort of see what the truck bed acceleration versus computed friction force on the spool relationship looks like. So to do that, just click, say, on line 14, right? Just click. In fact, you can click anywhere you like, anywhere you like. Once you've clicked somewhere around here, confirm that you see this blue strip over on the left-hand side. And once that blue strip appears, click on it, and it will run the section characterized by just this code. All right. So as I sort of scroll down, here's one of the outcomes that this section of code has produced. It's just a really simple plot that on the horizontal axis, it lists the truck bed acceleration. And on the vertical axis, it lists the computed friction force, assuming, of course, that there was no slippage. So I'm going to put it to you a hypothetical, yeah? So the hypothetical was, what if, hypothetically speaking, the static coefficient of friction for this spool truck bed combination was actually 0.1. And if we consider specifically the truck bed accelerating at 3 meters per second squared. With this as our scenario, was our assumption of no slip a valid one? All right, well, let's work the problem, yeah? So you and I both know that the maximum possible friction force that can be exerted onto the spool is the normal force of the spool, which is just its weight, mg, multiplied by that static coefficient of friction, yeah? And as it turns out, that happens to be 490 newtons, yeah? So let's have a look at our plot, and let me just sort of pop it out of the editor just so that we can look at a really big version of this plot. Oops, sorry. Here, this pink line represents 490 newtons. We said that our truck bed acceleration was 3 meters per second squared. And based on the no slip assumption, the friction force appears to be something of the order of 750 newtons. So we conclude that for this particular scenario, static coefficient of friction of 0.1, the truck bed accelerating at 3 meters per second squared, that our assumption of no slip on the spool was wrong. The spool is slipping. So this graphic has another really useful purpose, and it tells us what the maximum possible truck bed acceleration is in order for the no slip assumption to be valid. And I think you're already ahead of me. You can kind of see how to come to that conclusion. This 490 newtons, this is the maximum possible friction force that can be exerted on the spool. And that maximum possible force will actually occur when the truck bed accelerates just under 2 meters per second squared. Yeah. Alrighty. So that was nice. That was fun. Folks, any comments or even, heavens forbid, questions on what we've just done so far? If you're able to unmute your microphone, feel free and fire away.
For the task, will we be given a document like this, or will we be making a limited version of the code, like maybe just putting the variables there?
Dongbin, I think that one might be for you, actually.
Oh, okay. You don't really need to do any coding or programming, but for the variables, you can change the values of some variables for analysis.
Okay, thank you.
Yeah.
Alrighty, so folks, we're done with this no slip task. All right, so that's done. We do have one more task to do. So if I sort of get you to go back to your demo start here, please, script, and let's have a look at task 2. So in task 2, we will not make any upfront assumptions about the slip state of the spool. We will in fact compute what that slip state is. Yeah. So let's click on this link and let's have a look at our task 2 analysis script. Alrighty. So when you click on that link, I'm really hoping that it opened the task 2 analysis script file. And the main thing that you need to embrace for the next few minutes is we don't actually know what the slip state of the spool is. We need to determine what that is. All right, so let's scroll down our document. So in this case, we'll be utilizing the function that we looked at back in task 0, and we'll be invoking that function this time, not just with the parameters that we used in task 1, but we'll also be supplying the 2 coefficients of friction, the static coefficient and the kinetic/dynamic coefficient of friction. So when we invoke this function, bhfunc spool truck calcs, it will again return the normal force acting on the spool, the friction force acting on the spool, the angular and translational accelerations of the spool. It will also return a true or false answer, and that is an answer to the question, is the spool slipping? True or false? Is the spool slipping false? Well, it means the spool is not slipping. And if slipping is true, well, of course, it means the spool is slipping. So this will be the extra output that we return when we invoke our our spool calc function. All right, well, let's use it. Let's use this thing. So as I scroll down the script, you can kind of see that that we've got something that looks both similar and different all at the same time. So in this very first section of the script, we're again supplying numeric values for our spool mass, the truck bed acceleration. But you can kind of see that a selection of these parameters we've just highlighted with these interactive slider bars. So these kind of indicate that you know, out of all of the parameters that we could vary, we're going to be playing around with these 5 mostly. Yeah. All right. So I see that we've got some default values already dialed in. Let's perform the calculations for this specific scenario. All right. So what I want you to sort of just absorb is the truck bed acceleration is 3 meters per second squared. And these are going to be the numeric values for the static and kinetic coefficients of friction. Just a little heads up, note that this assert statement is just reminding you that the static coefficient of friction should always be greater than the value of the kinetic coefficient of friction. Alrighty, so look, let's run our calcs. Why don't you click on, say, line 12? Just click on line 12. Once you've clicked on line 12, or indeed anywhere in this section, you'll see you've got your blue strip, and click on your blue strip to run the calculations of this section of code. When you do, here are the results returned by our function. Apparently, the friction force that's acting on the spool is approximately 89 newtons. And look at this. For the scenario that we've just done our calculations for, it actually corresponds to a scenario where the spool is, in fact, slipping. It's slipping. So what I'd like to do now is I'd like to show you a Simulink simulation of this exact scenario. So we've already done our hand calculations. It would be interesting now to have a look at what an engineering simulation of this identical scenario now looks like. So let's scroll down to part 2 of this document. And look, it really only has 1 line of code. Can you just click anywhere in part 2 and then click on the blue strip just to sort of run the code that's in this section? And when you do that, it may take a little while for this next thing to appear on your screen, but it's going to open a Simulink model of this spool truck system. If this is the very first time you've launched the Simulink editor today, it may take 30 seconds, 45 seconds, as it is on my machine. But eventually, you'll get something that looks like this. So folks, I'm hoping that you brought along today at least 1 sheet of note paper and a pencil, because I'm gonna ask you to jot down some really important basic things. So the first sort of basic thing that I'm going to do, which will summarize the stuff that I want you to write down, is that if you notice this little keyboard badge in the sort of upper right-hand corner of your Simulink editor, when you click on that keyboard badge, it will actually open a documentation page that summarizes some navigation keyboard shortcuts. So I'm going to do that right now. So this is MATLAB's help browser. And it just sort of says, hey, if you click Control and, where is it? Control and plus. I think I might have scrolled past it. There it is. Basically says that, hey, if you were to press the two keys, the control key and the plus key, it will zoom into your model. If you click on the control and the minus key, it will zoom out of your model. If you click on your model and then hit the space bar, it will make the model occupy the full contents of the Simulink editor. And if you're lucky enough to have a Mac, you just simply replace the reference to control with your Clover key, or whatever it is that they call that key. So these are the three things that I want you to write down. All right. I'm really hoping that you've got that notepad, because it's going to be pretty unpleasant if you don't remember this. So I want you to write down control and plus. I want you to write down control and minus. And I want you to just write down spacebar. Let's have a play with what these things do. Yeah. So you have a Simulink model, right? So let me click anywhere in the blank part of the Simulink model editor, and let me now do control minus and control minus again. And if I keep pushing control minus, it'll zoom out to some limit. Clearly, this is too small for you to sort of understand what it is. So why don't you do the reverse now? Control plus. Control plus zooms in. And again, it has some maximum zoom limit. Clearly, this is not very useful. If you want the contents of the model to occupy full screen, just hit the space bar. So this is a Simulink model. And so far, all I've tried to convey is a couple of keyboard shortcuts for navigating that model. Really important. The next piece of Simulink model navigation a tip that I want to give you is down in the bottom left-hand corner of the Simulink editor. Here you'll see kind of a sideways chevron. Yeah. If you click on that sideways chevron, it will reveal something called the model browser. And the model browser simply gives you a tree view of all of the subsystems. We don't call them layers in Simulink, we call them subsystems. Yeah. But you can kind of see a tree node list of all of the different subsystems that make up this model. For instance, you'll see that there is a subsystem called the model. And if we click on the model, if I get you to click on that node, here's the sort of main modeling bit of this file. And again, if the block diagram is way too small, or if the block diagram is way too big, then this is where those keyboard shortcuts come in. Do your control minus, do your control plus, but the good old space bar, that wins nearly every single time. So believe it or not, this collection of blocks, this is how we represent the spool and truck bed system. It's Simulink combined with blocks from the Simscape multi-body block library. Yeah. So real quick, if I double click on this little red spool block, this little block allows us to specify a cylinder, right? We specify its radius, its length, and the block will automatically compute all of the inertias for this body. All right, so that's the model part of this file. Let's go to the measurements subsystem. So if I just sort of go over to my model browser and see that there's a subsystem called measurements, let's just click on that measurements subsystem. And again, if stuff looks really bad, just do the spacebar thing. And in this measurement subsystem, we've actually taken advantage of some sensors that allow us to measure exactly what it is that the spool's doing. We can measure exactly what the position, velocity, and acceleration of the spool is, as well as its angular position, velocity, and acceleration. We can also do some of our hand calculations and actually compare how our hand calculations compare against the same quantities that this engineering model produces. All right, so look, I think the first thing that I want to do is I want to run this simulation. So let's just get on with it. So within the Simulink editor, you should see, if I just sort of give you a little bit of orientation, you should see the simulation tab sheet. And then way down on the right-hand side of that simulation tab sheet, there should be a green circular run button. I'm going to ask you to click on that run button, and it should simulate your model. And I'm hoping that for most of you, what you also see is another window just happened to pop up on your screen called the Mechanics Explorer. And the Mechanics Explorer, as you can clearly see, gives you a CAD-like animation of what this mechanical system was doing over time. And there are clearly some playback controls at the very bottom of the screen that you can interact with. And if I just sort of call something out, to me, it looks like the spool completely left the truck bed at approximately 2.7 seconds. Let's see if we can sort of interrogate some oscilloscope time traces of this spool behavior, and let's see if we can sort of confirm that 2.7 seconds the spool left the truck bed really did happen. So I'm going to go back to my measurements subsystem, and you'll see that on the right-hand side of the screen, there are all of these pink sort of oscilloscope blocks. These pink oscilloscope blocks show us the time series values of signals of interest. So for instance, this particular scope block here shows us the normal force versus time, the friction force acting on the spool versus time, and it also shows us that true or false signal is the spool slipping. So if you double click, that's right, double click on this pink scope block, it'll bring up for you, a collection of time series plots. And hopefully some of the sort of interactive widgets up here make sense. You've got a magnifying glass that allows you to zoom in. This one is a little bit more sort of abstract. If you click on this guy, it will just sort of resize the time series plot so that it fits in the full window of the axis. So I'm going to do that now. It's better. So yeah, let's pick something to sort of play with, shall we? Here's the friction force time trace. And you can sort of see that on this axis, we've actually got two data sets that we're plotting. We've got the yellow data set and we've got the blue data set. So the blue data set comes from our hand calculations. These blue dots correspond to our hand calculations. And the yellow data set corresponds to the friction force computed by our engineering model, which did not use our hand calculations. And your conclusion from this is those hand calcs that we derived and implemented in a MATLAB function 40 minutes ago, they are in very, very close agreement to the yellow friction force computed by our engineering model, right up until the time when some event occurred. Let me just pull up the magnifying glass, and I'm going to see if I can zoom in on what's so special about this step change event. So this step change event occurs, it occurs at around about 2.6 seconds. So I think we're all in agreement that we know that at approximately 2.6 seconds, the spool did in fact leave the truck bed. And because there is no longer any contact between the spool and the truck bed, the friction force acting on the spool is 0. Now, we don't accommodate for that event in our hand calculations, but our engineering model does. And that's why you're seeing the difference between the blue data set and the yellow data set. So folks, let's do one more simulation, shall we? Let's go back to our task 2 script, and let's crank up the static friction value until it gets to the point where it says it is not slipping. And then let's do another simulation. So let me go back to our task 2 script. And I'm going to dial in my static coefficient of friction up to about, say, 0.7. So this is what I'm hoping, if you're following along at home, that you do. Let's just make this one sort of change. Let's just set the static coefficient of friction to 0.7. The fact that we've interacted with this slider, it has automatically rerun the calculations in this section. And our hand calculations now say that for this scenario, there is no slippage, and our friction force computed is about 163 newtons. Let's go back to our Simulink model. And let me click the green run button. The parameters that we've dialed in, those parameters are utilized by the Simulink model. So this simulation should reflect that brand new scenario where the static coefficient of friction was 0.7. So let me click the green run button. Let me pull up the animation. And at least to my eye, visually, it seems that the cylinder is performing more rotations. All right. What about the oscilloscope that we looked at before? The friction force calculated by the yellow model, again, is very, very similar to that 162 newtons that our hand calculations produced. Yeah. So I guess what you've just seen is we've used this independent engineering model, firstly for a scenario where the spool did slip, and the engineering model produced a friction force identical to our hand calculation friction force. And then we considered a second scenario where the spool did not slip. And again, our engineering model is predicting frictional forces acting on the spool comparable with our hand calcs. So folks, any comments or questions on this new thing? This new thing that is a Simulink model of the truck bed and spool system.
Yeah, on my scope model, I'm having trouble. I've either lost the lines or I've zoomed out too far to find the data. I've tried clicking that square with arrows that recentered. Would there be a function that removes the cyan and yellow line?
No. So look, just do this for me right now. Just go back to the green run button and just click the green run button, and then open up your pink scope. What do you see now after a fresh run?
For starters, the green run button. Oh, okay. It went to continue, and I clicked that, and now I have the lines back again.
Right, right. Yep. Great.
Okay, thanks.
No worries. All right, so folks, again, I'm just asking for any comments or questions. We've finished now this very first example, this spool on a truck bed sort of analysis. But are there any sort of final comments or questions on what we've done together so far? No. All right, that's not a problem. All right, well, let's clean up. I'm going to ask you to close the Simulink file that appeared. I'm going to ask you to close all of those script files that we had opened and sort of interacted with. So just close out all of those case study files. And once you've closed those files, I want you to go to the MATLAB desktop, the Home tab sheet, and I want you to click on an icon called Clear Workspace. And that will just get us nice and clean and ready to do the second and final case study for this morning. So, all of these MATLAB variables that are in your workspace right now from that spool and truck bed example, as soon as you click Clear Workspace, these will all be deleted. They'll go away. So if you can do that for me, you're almost ready to do that next example. Alrighty, so let's get back to the master or root level of today's workshop. So if I can just get you to just click on master. So the next folder that we're going to go into, which will finish us off for this morning, is this one. It's called Virtual Lab Principle of Impulse and Momentum. So you can sort of double click on this folder, and it should navigate you into that folder. Alrighty. So if you are following along at home, here's the very first sort of checkbox that you need to sort of confirm. When I look at my present working directory sort of folder here in the MATLAB desktop, you can clearly see that it says that my present working directory is Virtual Lab Principle Impulse Momentum. So that's a big tick. And if you are in fact in that folder, you will see these files. So that's tick number 2. All right, hopefully there's no guesses as to where we're going to start. I want you to find a file called task 0 start here, please. Once you've found this file, just double click on it to open it. Alrighty, so look, this is the system that we're going to play with today. All right, it's it's perhaps something that's close-ish maybe to a lab you might have done in an earlier year, but this is it. We've got an incline plank in yellow. At the bottom end of the incline plank, we have a spring damper connected to this green block. And I'm just going to sort of refer to this as the stopper. Why am I calling it the stopper? Well, because it stops stuff that sort of slams into it. So this stuff that potentially could slam into the stopper is at the high end of the incline plank. And we've just simply got a red mass denoted by M. And the red mass can roll down the inclined plank, and it will collide with the green stopper it will rebound off the green stopper, bounce back up the plank, and do it all over again. So this is the system that we're going to sort of consider. What I will say right up front is we will ignore any friction acting on the red cart, right? So we're living in this sort of la-la land where, you know, the friction effects acting on the cart are assumed to be negligible. We're ignoring friction effects on the cart. All right. So in this virtual laboratory, we're going to do three tasks. So in just a moment, I'll introduce you with the parameter definition MATLAB script. This is where we will type in numeric values for our cart mass, numeric values for how far was the cart at time 0 when we let it begin sliding, rolling down the inclined plane. So task 1 is just getting you really comfortable with this script that allows you to define numeric values for our apparatus parameters. In task 2, we'll actually open up a Simulink model of the apparatus and we'll perform a series of experiments. In the third experiment that we perform, we will log data. And that's important because we'll then take that experimentally logged data and we'll do an analysis of it in task 3. So that's what we're going to do. So let's start with task 1. So if I can just get you to click on the task 1 link, just click on that thing right there. So this is a MATLAB script, all right? And if I just sort of scroll down the MATLAB script, it's got some instructions, which I'm hoping that you read even after today's session this morning. And as I sort of scroll down it, you can kind of see that this is where we're creating some MATLAB variables to define numeric quantities. So at the moment, the angle of inclination of our yellow plank is 5 degrees. The starting position of the cart away from the stopper is 0.5 meters up the plank. Just some other things of interest. You'll see that we're able to also specify the stiffness of the spring that is associated with the stopper. Yeah. All right. So look, according to the instructions, there's nothing really for us to do here other than to run the script in its entirety from top to bottom. So if you just sort of follow the instructions here, go to your live editor tab sheet. It should already be sort of active, and look for the big green run button. There are lots of green icons, but look for the really big green icon, and just click that. So if you've done this first step correctly, you should see that in your MATLAB workspace, you now have, what, 5 MATLAB variables, yeah? These MATLAB variables are examples of a user-defined type called a structure. So if I sort of give you a little bit of a look at what the param variable looks like. So here's this MATLAB variable called param, and it has a nice sort of field hierarchy inside it. And one of the fields inside this param variable is a field called theta_deg, and it has the numerical value for the angle of inclination of our ramp, our plank. Yeah. Just something else to call out. Inside this param variable, we also have information about the stiffness of the stopper, just for example. If I just have a bit of a sticky beak at another one of these workspace variables, let's have a look at the variable called env. which should be short for environment. You can kind of see that the N variable, well, it only has one field, and this number probably looks very familiar to you. Earth's gravitational constant. Alrighty, so task one was really, really simple. We just ran the script, and it defined in our MATLAB workspace a collection of MATLAB variables, which has categorized our experimental apparatus. So this, folks, is the experimental apparatus. So let's play with this apparatus by way of a Simulink simulation. So if I go back to my task, my start here task, so let me just get you to click on this guy again. And now let's open up task 2. So let's just click on task 2. All right, so here's our task 2. We are indeed going to explore and, well, we won't be doing any model editing or creation, but we will definitely be exploring and doing some experiments. So yes, as I sort of scroll down the script, it's saying, hey, your MATLAB workspace had better look like this, or if it doesn't, you need to go back to task 1. I'm going to give myself a big fat tick. I've confirmed that that is in fact correct. And then the instructions say, do not run this script by clicking the run button. Good to know, good to know. Instead, follow the instructions of each section of the script. All right, so let's pretend that we're going to obey this. There is a video for you to watch in your own time. We are not going to do that this morning. And also this morning, we will not be asking you to complete the partially completed Simulink model. Instead, I'm going to get you to go straight to the break glass in case of emergency section. And I want you to click on this link. So just click on that guy. And this should open another Simulink file. And when this Simulink file appears on your screen, if it looks like your face is pressed against the window and things that are either too close to you or too far away, you guys remember that do the Control+, do the Control-, or the spacebar. So this is the Simulink in brackets with Simscape model of our apparatus. If your model browser is not open, then go to the bottom left-hand corner of the model and locate that chevron sideways icon and click on it. And when you click on that, it will reveal the model browser. And you might recall that the model browser gives you a nice sort of tree view of all of the subsystems or layers that make up this Simulink file. So right now, you can kind of see that we are indeed looking at the model subsystem in this file. But I want you to have a look at the sensors and data logger subsystem. So if you can just sort of click on this thing, sensors and data logger. And it's probably doesn't look very nice, so do the space bar. This sensors and data logger sort of system, it has an oscilloscope that after we run our simulation, we'll be able to view the position and velocity of the red cart as it varies over time. And more importantly, we'll also be able to view the impact force exerted by the stopper onto the red cart. But look, first things first, let's run an experiment. So I'm going to go back to our MATLAB script. And I want you to go to the task 2 script and just scroll all the way down to experiment number 3. So experiment number 3, we will configure the apparatus such that the plank is at 5 degrees incline. The red cart starts half a meter up the ramp. And we're going to be using a spring stiffness with our stopper of 10,000 newtons per meter. So these are the 3 numbers that we need to now dial in to our parameter script. Yeah. So let's just click on this link to open up our parameter script. And let's scroll down the parameter script and let's dial in. What were the numbers again? I think for experiment 3, the angle of incline was 5 degrees. And I think we said that the red cart will start half a meter away from the stopper. And was the spring stiffness 1,000 newtons per meter? No, it was actually 10,000. So I need to interact with this drop-down box, and I need to choose 1e to the 4. So here's how you can dial in the appropriate apparatus parameters for the experiment that you've been asked to conduct. Yeah. So once you've dialed in the exact parameters for the experiment that you've been asked to do, we're not going to do all of these experiments with you this morning. I'm only going to do the last one. So these are the values that we just had to make sure were dialed in for experiment 3. Done. All right, we've just done that. Now let's go to our Simulink model and let's run the simulation where the apparatus is characterized by the parameters that we've just dialed in. So if you click this green run button now, it will run your sim for our specific experimental scenario. So that's the experiment that we just did. And again, I might just interact with some of these replay widgets at the bottom of the viewer, just so that we can replay it. Yep, that's what I would expect to happen, right? So there are no surprises that this engineering model is producing something that looks very, very sort of relatable. So let's have a look at some time series traces. All right, so we've just visualized what the apparatus did for our specific scenario. Now let's have a look at some of the measurements that this model has been instrumented to make. So we're in this sensors and data logger section of the model. And just some things that I want to call out. The position and velocity time traces that I'm about to show you were taken from an inertial observer with origin 03. So the x-axis of the 03 observer is parallel to the inclined plane. The y-axis of the 03 observer is perpendicular to the inclined plane. But this origin 03 is where our observer with his binoculars was based. So this is the guy telling us what the position and velocity of the red cart is. So yeah, let's just double click on this pink oscilloscope block and let's look at some time series plots. Now, folks, if on your laptops, the sort of top of the figure window is sort of truncated by the top of your screen, as is on mine, I'm just going to sort of show you just some standard sort of Windows book housekeeping that just allows you to sort of recover the full figure. There it is. Ugh. That's better. All right, so these three axes show us the position of the red cart, the velocity of the red cart, both of those quantities relevant relative to our inertial observer. So just stare at those two things for a moment. Is this what you think you just saw in the animation? The initial position of the cart was 0, and at some point in time, the cart got down to about 0.5 meters, and then it was abruptly sort of turned away, and then it started to climb back up the ramp. Yep, that time series plot is immediately sort of relatable. What about the velocity plot? Let's have a look at the velocity plot. The red cart was initially at rest, and then it started to get faster and faster and faster. I wonder why that is, by the way. And then some event happened where it suddenly went from having a negative 0.9 meters per second velocity to almost instantaneously having a positive 0.7 meters per second velocity. I wonder what was responsible for that. And what about the bottom plot? So the bottom plot, folks, is the force exerted onto the red cart by the green stopper. And you can clearly see that for most of the time, that force is 0. Except, of course, at the very moment when the red cart collides with the green stopper, where you can kind of see an almost impulse-shaped sort of force history. All right, so this data that we've just collected, this time series data, we're now actually going to analyze this in task 3. So before we move on to task 3, does anyone have any questions or comments on the experiment that we've just used this Simulink model for? No? All right. So this is the experiment that we just did. And in just a moment, you will again be looking at these plots of position, velocity, and impact force. So you know where the data came from. All right, so let me go to my start here, please script and get you to click on task 03. Let's analyze the data collected from our experiment. Click on task 3. All righty. So task 3, folks, let's work our way through this. So here are some instructions, which you're definitely welcome to read after today. And it's saying, hey, have you really done the task 2, in particular experiment 3? If you have, your MATLAB workspace should look like this. In particular, you'll probably have another MATLAB workspace variable called mySimResults. Do you? Do you really? Why, yes, I do. So this is the data that we've logged from our experiment, the data that came from our Simulink simulation. All right, so we say, yes, we're primed and ready to do the analysis. What do I need to do? Well, do not run this script by clicking the run button. All right, I get you. We're going to work our way through each of these sections of the script one at a time. All right. So first of all, a little bit of a refresher about the concept that we're going to be applying in this analysis phase. Do you all remember the principle of impulse and momentum? So as a refresher, look, it always starts with Uncle Newton. It always does, right? So Newton's second law, the sum of the forces acting on the red cart is equivalent to the mass and acceleration of the red cart. Let's write out the acceleration as the derivative of velocity with respect to time. And let's move some things around until we get this expression, which ultimately can be integrated. Yep. If you integrate the left-hand side of that expression, it's really easy. Yeah. If you integrate the right-hand side of the expression, it requires some knowledge about the forces that were acting on the red cart. And aren't we lucky that that we've got a sensor in our experiment that actually told us at least the impact force that was acting on the red cart? So the principle of impulse momentum gives us some expression like this. And let me sort of add a little bit more commentary. So let's say that prior to the red cart impacting the green stopper, the nanosecond before that impact occurred, we know the velocity of the red cart. The nanosecond that the red cart disengaged from the green stopper, you know, the impact event has happened, and now the red cart has moved off the green stopper. The nanosecond that occurs, we know also the velocity of the red cart. And relating those two things is the integration of all of the forces that are acting on the red cart during that event. So let's see if we can prove this statement of the principle of impulse and momentum. So what we're going to work towards is, I'm going to say that we can measure this. I'm going to say that we can measure this. So if we know everything on the left-hand side, if we know that, does it indeed give us this? That's what we're going to work towards over the next 10 minutes. Yeah. All right. All righty. So let's just scroll down our script and let's click on line 1 of the script and click on the blue bar. This will just load into a MATLAB. Sorry, it will just echo in the script some of the time series data that we logged from our experiment. And you can kind of see at the moment it's stored in a MATLAB variable that perhaps looks a little bit intimidating. It's not really, but it might to a first timer. So what I propose to you as we scroll down to line 3 and execute this section is, let's just strip out that time series measurement data into a much friendlier looking data container called a table. So in a table, we have named columns. There's a column called time. There's a column called pos_m, vel, and there's also a column that is our impact force. So all of this data is now stored in a MATLAB variable called my data table. All righty. So folks, does anyone know how to plot 2 arrays in MATLAB? All righty. Well, let's do that. So you can kind of see that the block of code from line 17 to 13 is actually commented out. So I'm going to highlight those 7 lines. And then in my live editor tab sheet, you'll see that there's this little icon right here. And if you click on that icon that I've just sort of zoomed in on, it should uncomment those 7 lines of code. So let's do that. All righty. So let's just complete this. So what I want to do is I want to be able to plot time versus the position of the cart. So it's already sort of partially done for us. So line 7 is already done. Let's finish off line 8. So line 8 needs to be this, my underscore data underscore table dot, and the column in the table that I want to plot is pos underscore m. Now, for those of you that might be new to MATLAB, if we don't put a semicolon at the end of our assignment statement, it will just echo the contents of that line to the screen. Sometimes you want to see it, sometimes you don't. I'm going to say this is an instance where we don't, so I'm just going to put a semicolon there. Line 10 will spawn a fresh figure that can capture plots, so there's nothing to do there. But line 11 is where we need to specify our horizontal data and our vertical data. So here we're going to plot the time array will be the horizontal axis data. So just type that in. And the vertical axis data will be the position underscore array. So just type that in. So here's what this line should look like. And there's one more edit that we need to do, which is just sort of putting a vertical axis label on our plot. And really that's, you can write whatever you like, but given that this is a plot of position of the cart in meters, that might be a sensible label for the vertical axis. So folks, here's what you need to do in order to complete this section. Make sure this line looks like this. Make sure this line looks like that. And you've got a little bit of artistic license as to what you want to type in here.
Y label's missing a semicolon.
On whose screen are you talking about?
On your one, the line that you just wrote. Does it need a semicolon?
On line 13.
The final one, yeah.
No, it actually doesn't. Well, you can put it there. You can put it there. In fact, look, I won't, but you can. But Y label isn't returning anything, so I've got nothing to suppress. But you're welcome to put a semicolon there if you want to. So once you've made those edits, just do your old blue bar trick. Move over to the left-hand side of the screen and click on that blue strip. And hopefully it creates a plot that looks very, very familiar to you. Very familiar. This is indeed the position of the red cart versus time. All right, let's scroll down to the next section. I'm going to click on line 15 and I'm going to run it. And all this section does is it just plots all of our data. And yes, those three axes look very, very familiar from our experiment. So let me just sort of scroll down to the next section. And the next section is about, hey, I just want to focus on the interval of time immediately before the first impact event and immediately after the first impact event. So if I just sort of pop this out, this plot, make it as big as I can, and if I just use some of the visualization tools, this is kind of telling me that, you know, if I was to pick an event that was somewhere close to 1.0, you know, that's just before impact. And if I was to pick a time at, say, 1.12, you know, that's definitely after the impact event. So these are the two numbers approximately that I want to dial in to the next bit of my script. So what I'd encourage you to do is maybe just fiddle with these just a little bit. All right, so let me fiddle this to maybe 1.05, and I might fiddle this to being maybe 1.4. As you interact with those sliders, it's producing for you a plot that shows the data just between those intervals in time. And yes, I concur that that has sensibly bracketed my first impact event. So good. As I scroll down this, you might also see a duplicate of that position, velocity, and force plot, but it's just putting a red and green dot, hopefully almost bang on where the impulse started and stopped. And again, you can visually confirm that. So as I keep working my way through the script, this next session looks interesting. MATLAB can numerically integrate a curve. You don't even need to give it the parametric form of the curve. If all you've got is just the data of the curve, then MATLAB can use a function called trapz. So just to be crystal clear, I'm keeping an eye on the time. I need to wrap this up in 3 minutes. To be crystal clear, if we were to uncomment lines 36 and 39, just like we did before, and if I was just to type in the appropriate MATLAB variables TList and GList, then what we're sort of doing here is, here's some example time data, here's some example sample data. And if I just give the trapz function just the data, it'll still compute the area underneath that curve. So here is the numerically computed area underneath this pretend data set. And the really sort of warm, fuzzy feeling is that that numeric value is very, very similar to what you would have computed in your high school calculus class. So that's all trapz does. It computes areas under curves where the curve is specified by data. And I think you can kind of see where we're going with this now, as the final sort of bring it home, is now all of the pieces are in place. And what we're going to do is we're going to do this operation. We're going to say, if I compute the area underneath our impact force time series curve, right? trapz will do that for us. Now, if I then add to that computed area this thing, where recall V1 was the velocity of the red cart the instant before impact. And if I then sort of divide all of that by the mass of the red cart, I will get a prediction for what the bounce back velocity of the red cart should be. I will then compare that prediction velocity against what I actually measured in my experiment. And I'm hoping that those two numbers are really, really similar. So let's run this section of code. So when we do that, it's sort of predicting that the bounce back velocity is 0.77 meters per second. But what we actually measured from our experiment was 0.74 meters per second. It's close. It's, it's within, say, 4% of the measurement value. But it's, I mean, are you happy with that? Are you happy that that this prediction velocity is within 3% of what you measured? Do you think that that's a good result? Or are you sending up some flares that it should be a lot closer than that? I'll give you a hint. In evaluating this, there was one fundamental force that did not find its way into this thing. We definitely included the force of impact exerted onto the red cart from the green stopper, but there's a fundamental force that we did not include in this calculation. Would anyone like to maybe cite a reason or cite what that force is? If you were to draw a free body diagram of the cart at moment of impact, you would definitely have one force that denotes the contact force, but surely there's another force that you draw on your free body diagram. Anyone? Gravity. Well done, Chris. So I put it to you that what we should have superimposed in our f variable was the effect of gravity. Yeah. So let's sort of do that together right now. All right. So let's just edit line 43, and let's type this out together. You ready? Param. Oh, sorry, plant. Was it called plant or param? Param. It was called param. So param dot m times m dot g times the sine degrees. MATLAB has a sine function that allows you to give degree input arguments. You need to specify d as the name of the extra character in the function name, sine d. And I think the slope was at an angle of param dot theta dag. So I'll get you to sort of digest this. So mg and sine d, that is the component of the gravity force acting parallel to the plank. All right. So I reckon if you rerun this section of code, you'll get a much, much closer comparison in the predicted velocity and the measured velocity. Give it a go. Give it a go and see what happens. Yeah. How do you like those apples? So now that we've included all of the forces acting on that red cart, we're predicting an exit velocity of about 0.741, and that compares very, very favorably with what we measured in our experimental apparatus. So folks, that's it. All I wanted to do is just make sure you were comfortable opening these files, driving them, and interacting with them. And I think we've just finished in the nick of time. But look, any questions or comments on what we've just done together? No? Okay. Dongbin, over to you.
Yeah. Okay, thank you very much, Bradley, for your guest lecture. I just like to add a few comments. As you can see, most problems in this mini project are simple, so they may be solved manually without MATLAB. But here you can see MATLAB help you to do calculations, give you a great display of results for analysis, and provides a beautiful visual presentation for you to see the motion of a body directly without involving costly and time-consuming physical simulation. For complex problems such as the real engineering problem you may account in the future, numerical computation is often necessary, and you may not solve them manually. You will need the assistance of a computer equipped with suitable software. And regarding a programming language and a numerical computing environment, MATLAB is currently the most powerful tool for this purpose. But I have to clarify one thing. MATLAB's purpose is not to provide you with a solution. You need to be able to do a clear analysis, including drawing diagrams, define boundary conditions, and defining all parameters before you can ask MATLAB to work for you. So that's the purpose of this subject. And Bradley's guest lecture taught you how to solve a problem by thinking in a way of MATLAB. Okay. Okay. So do you have any questions? If no questions, I think we
Hey, Dongbin, I got a question.
Yeah.
I just I still don't really know what we're meant to be doing then for this assignment. Because it seems like all the programming's done for us. What are we meant to actually be doing?
Yeah. Sorry, I can't hear you.
Oh, can't you hear me? Why is it not doing this? If I go, you can hear me now?
Yeah.
Yeah, okay, cool. Yeah, I'm not totally sure what we're meant to be doing for the assignment. Yeah, like if all the programming is already done for us, what are we actually meant to be doing?
Oh, okay. In this assignment, you will need to do all the tasks, including 2 problems and 2 virtual labs. And we will ask you to provide your manual solution in your written report. And also, you will need to do analysis based on the results you can get from MATLAB.
So we need to do all those problems we need to do manually as well as using MATLAB and compare that or something.
Yep. In your manual calculation, you will only to use the certain values for some parameters, so you can get a certain final answer, like some questions you have solved in the tutorial class and also in your quizzes. Then you will use MATLAB to verify the answers you can get in your manual solution, manual calculation. But in addition, because using MATLAB is a powerful tool, so you can change the the values of a lot of variables in a problem in MATLAB easily. So you can do quite a lot more, such as analysis. So all this should be in your written report.
Okay, so then another question. So where do we get the variables from the manual calculations? We just take the tasks that are in MATLAB and just do them all manually as well?
Yeah. In the written report, you will need to establish the equations for a problem, and then you can assign a value to a variable, then you can get a certain value for your final answer, isn't it? And then you can use the MATLAB to do the calculation for you and to verify the answer you can get in your manual calculation.
Yes, makes a little bit more sense. Thank you.
Yeah. So this task will be more difficult than you have in the quizzes or tutorial problems. Okay. Any more questions? Okay. If no question, let's thank Bradley, and we will see you next week. And Bradley will taught you how to solve another problem and a virtual lab using MATLAB. Okay. So thank you very much for your attention. Thank you, Bradley.
Thanks, Dongbin. Thanks, everyone. See you in a little bit.
Yeah. Thank you. Bye.